My guest today is Professor Thomas Shutt, who is Professor of Particle Physics and Astrophysics at Stanford University. One of his recent areas of focus is the detection of dark matter. Welcome, Tom.
Mm-hmm.
So I want to go a little bit back in history about dark matter. This idea has been with us for a long time, I understand, right? Was it somebody from Caltech who first sort of measured the rotations um, uh, of the galaxy stars and concluded that there must be something wrong there? So when did we first detect there's a problem?
Yeah, I think it's just interesting. It kind of came in pieces. People often point at a guy named Fritz Zwicky, who was a bit of a character at Caltech, and that's probably who you're referring to. One of the issues is that, the basic way we know about dark matter is by its gravitational effect. And a simple way to think about it is, if you take just like the solar system, the Earth is a certain distance from the sun, and it orbits in a certain time. And that's just like exact. And the Newton's laws that he figured out in the 1670s just give you that. And Jupiter is a lot further out, and the amount further out that Jupiter is and how much slower Jupiter moves all matches gravitational equations. The issue with then, and dark matter is not observed from that. Dark matter has been seen by looking at much bigger systems, namely a galaxy, or in the case of Fritz Zwicky, it's galaxies tend to come in groupings, clusters they're called, of maybe a few thousand galaxies, and they're all sort of orbiting each other. And then the problem is there's all sorts of challenges when you're looking at these things through these telescopes that are distant to figure out the distance out there and to figure out the velocities. And so dark matter sort of emerged. Very early evidence, people like to talk about Fritz Zwicky, but frankly, he basically he studied a system, and things were orbiting too fast, given how much mass he thought he saw in it. Which is to say, it's as if the sun were suddenly heavier, the Earth then, to stay in its own orbit, ought to speed up, or if it didn't speed up, it would get pulled into a closer orbit. Okay.
Yeah.
If suddenly the Earth were so the balance of how it's orbiting tells you how much the sun weighs. And effectively, he looked at a system of orbiting galaxies and said they should weigh more than the velocities of the galaxies indicate. But his data was, frankly, they couldn't be measured back then.
Right.
And really, in the 80s, studies of how galaxies rotate, galaxies alone, became conclusive. By the late 80s and the early 90s, there's a woman, Vera Rubin, who in particular really spearheaded this. And there was a kind of a slow set of people accepting it, various people to varying degrees over time. The thing is, now it is seen on a huge number of different, in a huge number of different astrophysical measurements on a vast range of length scales, where the size of a galaxy, which is already immense, is the smallest scale. And there's these structures which are much larger, clusters of galaxies, which I've mentioned, and things that are seen in this view of the Big Bang we have in the cosmic microwave background, which measures even larger scales, these really enormous scales in the whole universe, basically. We can see that whenever we can measure the influence of gravity on, what we see now are mostly galaxies, but we can see how the galaxies are moving in response to the gravity locally. In every way we do that, the answer is there's a whole bunch of mass there exerting a gravitational pull, and we can't see the mass. We can't see it in stars. We can't see it in any dust or gas. And that kind of overwhelming amount of evidence now, which is a long, long, long story, is really why everyone is convinced, almost everyone is convinced there's dark matter.
Almost
and
everyone.
the few skeptics who aren't convinced there's dark matter certainly agree there's a problem, and they think, well, maybe we can solve it by modifying gravity. That gravity is different on the big scales than we know it is. We know it's super exquisitely accurate on the scale of a solar system, but maybe on much larger scales, our understanding of gravity is wrong. And there's a small set of people that are pursuing that approach, but most people think it's a new form of matter.
Yeah, so when Vera Rubin came along and conclusively shown that there's something wrong with the motions, the way
Right.
that we understand them, people seem to have, excluding the small community, talking about, I think it's called MOND or something like that, modified
That's right.
Newtonian
That's
dynamics,
right. That's right.
that there's something out there that is. So the way I understand this, Tom, is that so if you think about the Milky Way galaxy, the closer you get to the center, the faster things will rotate. But we
Right.
have some sort of a disk type feature at the center, right? So so as we go away from it, we would expect in Newtonian dynamics that things will slow down, but we
Right.
don't see that in the measurements, right? Things sort of the velocity of things away from the galactic nuclei is about the same all through for a long range of space, right? Is that the issue?
That that's absolutely right. And it's kind of an odd thing. The fact that it actually the velocities are pretty much the same, even as you go further and further out from the center of the galaxy, is a little bit of a numerical accident. The real thing is that should have been falling off. In our solar system, the further you are from the sun, the weaker gravity is, and so then sort of the weaker, if you will, the centrifugal force, and you simply move in a slower orbit. And it's kind of just that's exactly how it is. And once you get out beyond the kind of visible edge of the galaxy, galaxies are messy objects. Like, the thing about the solar system is the sun is pretty much it acts just like a single point, and it's just like perfect equations that you can learn in high school. Galaxies, this big, messy, extended object, hard to measure all the components of. How do you know its mass? Well, you got to kind of have a good idea of the mass of all the stars and add all that up. A lot of messy stuff. Took a long time to where people thought they had all that kind of correctly figured out in order to talk about this question. But the answer is yeah. Once you're out beyond the edge of it, all that messiness doesn't really matter. You've got a mass in the center, and you got something out beyond. And there are these things. There's these gas clouds, which we can tell are bound to the galaxy, but they're more or less isolated objects. And it's kind of like the sun with planets. It's almost that clean. So really, this prediction that the further out you go, the slower they should be moving is pretty solid. And yet it just isn't there. It just that the data resolutely turns out, yeah, it's actually a flat thing. And it's basically as far out as anyone can measure, which means how faint a little gas cloud have people been able to find using really fancy radio telescopes looking at this faint emission from gas clouds. And they use the Doppler shift, by the way, the exact same thing that the police get you for the radar. They use the Doppler shift, blue and red shift. Is it moving away from us or towards us? And that's how they measure these velocities and all that. And it's come into focus. And the answer is, by God, about 10 times the mass in normal stuff is there somehow in dark matter.
So it's not just the Milky Way. We observe this in a lot of galaxies by now, right? And we see this sort of the same pattern. But I was, without knowing anything about this, Tom, there's something curious about this sort of a flat profile going a long distance.
Right.
At least on the surface, it implies, well, don't you have to have, so what's our conjecture about sort of the mass density? How the mass density is growing inside the galaxy.
Right. Well, yeah, that flat, the fact that they tend to be flat then requires that the dark matter actually have a specific profile in terms of the density falling off with radius. And the fact that all the galaxies are pretty much the same. In fact, one of the MON people is actually a friend of mine, and he's really kind of focused in on that. And to him, there's this elegance in just tweaking the equation in one particular way of gravity, and it can explain everything. If it's in the matter, the answer sort of has to be that the way gravity made the galaxy grow in the first place, right? How did a galaxy even exist, right? The key point, I know you said you've had some early cosmologists talking, right? Key idea is that the universe started out super uniform, and it was a little bit of lumpiness. And now we're talking early in the Big Bang, and wherever it was a little overdense, a little heavier, random, from the beginning, those places grew. The places that were less dense lost matter, and the matter kept falling into the heavier places. It has to be that as a natural consequence of that process, the the clumps, which are the dark matter, that are the kind of the seeds that are the core of all galaxies. I shouldn't say core like in the center, but they were the thing that formed first. Dark matter fell in, established a place where there's extra mass. The normal matter fell onto that. That became a galaxy. That process has to be fairly regular because all these curves of how the velocities of things are working in the galaxies are all the same.
Yeah.
And so that it does seem, actually, maybe it should be comforting that they're all similar. It's basically saying the way gravity influenced all these galaxies works out to be the same. And maybe that shouldn't be a surprise.
Yeah, so it's sort of universal. So that makes sense. So in some sense, could we conclude that we could not have had galaxies the way that we observe them without the dark matter? I mean, this is not a small piece of the puzzle, right? I don't know what the right numbers are, Tom, but 5% approximately of baryon matter, something like 25 to 27% dark matter. So this is not a small proportion. Yeah.
The universe would look nothing like it is today if there weren't dark matter. Not at all. Not even remotely close. In fact, it's even more than, I mean, the early universe was very, very uniform, this hot fireball, just like the center of a flame. It had a little bit of texture, graininess. Some places were a little denser than others. Of course, it's expanding rapidly and the density is dropping rapidly because it's exploding. It took a while before this effect of the places that were a little bit denser really start to just gravitationally accumulate matter from the regions around them. And those finally became the places that are galaxies. And then the galaxies, there's all this gas and such. And then that gas collapsed and formed stars, et cetera, et cetera. The dark matter actually caused that process of the gravitational collapse that grew everything. And if there were no dark matter, in some sense, the universe would be much less far along in having done that. And today, the universe would be much more just a bunch of boring gas and the beginnings of galaxies. There'd be galaxies, but many, 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 many fewer of them. Much, much less likely that there would be solar systems that were 4 billion years old, 4.5 billion years old, et cetera. Yeah. It really would be a very, very different place if it weren't for dark matter. Dark matter is, you say, like, what does the universe look like? The normal matter is almost irrelevant. It's the dark matter. It's the Big Bang and the dark matter and dark energy. And those are what matter. And we're kind of like a little bit of flotsam and jetsam in the story that's just kind of sitting there. We're icing on the cake.
Yeah, so, sometimes people say, well, this is sort of symptomatic of fine tuning. It's like God is sitting there and created universe and sprinkled on the 26% dark matter on it, just to make it work. Do you see any arguments for fine tuning here, or this is just totally random?
No, actually, it's interesting. People don't typically talk about this because I don't think it's as fine tuned, but at some level, it is yet another thing like that. Yeah, indeed, there are many things that had to be just so. Dark matter had to be maybe not just so, but certainly so for us to be like we are.
Close enough some factor.
Right.
I have to say, as an engineer, I find MOND sort of attractive. But if MOND is a null hypothesis, do we have enough evidence to reject it?
Well, actually, it's interesting. If you take the evidence at the scale of galaxies alone, I think then MOND would be much, much, much more believed in. Because actually, it's remarkable how well it works for the scale of galaxies. The reason people tend not to like it, we don't have a clear factual way to say yes or no. But the reality is, when you talk about the early universe that we can observe through this cosmic microwave background, which is exploring a pretty darn early time, and also not just at the galaxy scale, but even today, we can see structures on very large scales, and there's all this modeling of how that grew. All of that requires gravity to have been different on this other set of length scales and much earlier in time. And no one has come close. Well, okay. In general, it is very hard to construct a fully consistent theory of gravity that is just like normal gravity in the scale of the solar system, is somehow different in the scale of galaxies, but then not different again in all the larger scales. And also just, general relativity is a fantastically successful theory. It has all this intrinsic beauty, which it's nice, but that doesn't mean it's right. But just by hand, like tuning MON by hand violates, that you have to add a whole other sector of physics to do that and not violate all sorts of things about energy conservation and things like that. So to come up with a completely consistent with all we know about modern physics theory of gravity that does everything you need to do to simulate dark matter is very complex, and no one's really done it. And so then you kind of resort to, do I really think it's more, is it Occam's razor to say, well, look, there's a new form of matter? Or is it Occam's razor to say gravity has changed in a way that I can easily tune for one small part of the problem, but is really, I don't know how to tune for the rest of it. And that's, I think, why most people say, the notion that it's just a new form of matter. Plus which there are a handful of observations. There's this famous bullet cluster where two clusters of galaxies sort of ran into each other. And if you're the stars, what does running into each other mean? It doesn't mean anything, in fact. You just miss. You have an overall gravitational pull, but you only feel the gravity, and it's at a distance because the stars are, still, space is mostly empty. The diffuse gas actually kind of collides and has kind of a shock behavior. And that whole system has been mapped, and you can tell that the matter is not where the gas is. And it turns out the gas dominates the cluster. So the normal matter did one thing, and the overall matter, which is we call the dark matter, did something else. And a lot of people say that kills MOND. My really theoretically bent friends say, no, you can't kill a theory like that. We'll make a theory where we're modifying gravity, and we'll modify gravity so that it does all that. And here's a paper. I'll put it in the preprint server tomorrow. And they spend all night, and they got a paper, and boom, they calculated it. It's just at that point you start to get into a question of, wow, there's all this complex behavior and this huge variety of length scales, and simply introducing a new component of matter solves it all, versus do I really think it's that gravity is, unusual enough that it's kind of tuned and looks kind of like the presence of just a new form of matter in this whole variety of contexts.
Yeah.
And it's really just, until we either directly measure the dark matter or not, it's not clear that you can ever answer this question.
Yes, so the dark matter appears to be sort of the dominant hypothesis to explain this. And I understand that, Tom, there are different candidates for dark matter. We haven't found anything yet.
Right.
There's hundreds of orders of magnitude. So from, say, axions at 10 to the minus 20 to stuff that you work on, which is WIMPs, which is sort of is it the proton size type thing?
It's the thing that's particles that are as heavy as normal atoms.
Normal atoms. And then there were ideas from the primordial black holes, which might be tens of masses of solar masses. So in this whole spectrum, there are a lot of experiments. I know that we have done a lot of experiments. We have looked for a lot of things. We haven't found anything yet. So why do you focus on sort of the middle of the spectrum, meaning WIMPs? So before we get into it, what is WIMP anyway?
Weakly interacting massive particle. Maybe I should back up and say, particle, physics faced with the idea that, hey, wait a minute, we don't know what a huge form of mass in the universe is, the dominant form of mass in the universe is. How do we react? And I think there's a strong bias guided by history here. It doesn't mean we're right in thinking this way, but there's a reason. And the history is that, going back to the discovery of understanding of radioactivity at the, beginning of the 20th century, leading to, atom smashers and nuclear energy and all that, right? And particle accelerators. We have learned that in addition to the basic building blocks we know and love, atoms, which are neutrons and protons and electrons, in fact, there's a whole zoology of particles which can be created and which do exist. And now, almost all of them, and you do this by colliding particles at high energy. We figured out how to make cyclotrons and later more sophisticated machines, generically atom smashers, right? And we typically, it's like a proton, and you accelerate them to super high energies where their, Einsteinian mc squared mass is much bigger than their kinetic energy is much bigger than that mass. And basically, when they collide, you can create new particles. And in fact, there's a whole range of particles, and we've called the standard model of particle physics. And there's like 10 fundamental particles, and then they exist in various states that make literally dozens and dozens, hundreds of other particles. And it just so happens that almost all of those are very short-lived and decay. There is a new one, the neutrino, which was hypothesized in the 30s and then fairly shortly thereafter found, that's stable. And so there's even an exotic particle, the neutrino, which we create in atom smashers, which is stable. And so when the dark matter story came along, it has been very natural for us to think, look, obviously nature handed us the reality that on the subatomic level, there are many, many, many particles that exist. The ones we've been able to create with accelerators have all been unstable. They break down into normal particles eventually. But maybe there's some new class of those particles that are stable, and we haven't discovered them yet. The generic reason would be that they are heavier. They require more energy than we've been able to build in an accelerator to create.
Yeah.
But in the early Big Bang, which was a fireball of unimaginable energy, and if it wasn't high enough for you, go back another, fraction of a time since the beginning, and it's hotter. And if that's not good enough for you, go back a factor of 10 back. At 1 second, it was pretty darn hot, but at a tenth of a second, it was 10 times hotter. That's not good enough for you. Go back to a millionth of a second. It's a million times. It's probably like a million cubed or something. I forget how those scaling laws work, right? Yeah. So all that stuff had to have been created. Anything that could have been created that we can create in an accelerator now just was in the middle of the plasma of the Big Bang. So ever since the dark matter idea came out, the particle physicists have all been saying, look, it's probably a particle left over from the Big Bang. And the way to think about it is let's start to think about what are the big holes in our understanding of particle physics. And essentially, there are two big holes which immediately people started thinking about. One solved something called the mass hierarchy problem. It solved a big theoretical ugliness in what's otherwise a very beautiful model, the standard model of particle physics. There's actually a lot of ugly calculation, which was under very generic conditions early in the Big Bang. If you say, how could I very easily create dark matter through something called the Freezeout process, which is a big story, but let me just say it's a simple argument. It turns out that you get one prediction. You get a prediction for the size of a particle, and that size happens to be the size of a neutrino. And the neutrino is a generic size scale of all the particles that we know about. It's the size scale of the smallest particles we know about, but that's what it is. This argument in the Big Bang, if you ask for a generic way, you try to make a generic mechanism for why. Sorry, let me back up just a tad. I said that you can create in the Big Bang, there's the early plasma of the Big Bang, all sorts of exotic particles that we created accelerators routinely, like the Higgs you heard about, in a lot in the news recently. All of those particles would have existed, but then what happens when everything cools down and the energy of each collision is not enough to create those particles anymore? Those particles, particle, antiparticle, they find each other, they annihilate away, and they're gone. And then the question is, well, and that's we know that has how the universe was. In the early Big Bang, there was a vast amount of matter, antimatter particles, like a soup of that stuff. And as we cooled down, all of those exotic particles, they found their mate, if you will, and are gone. Yeah. You always have to create if you create matter out of energy, you always have to create an equal particle and antiparticle. And then strictly those, and that's real strict bookkeeping. And if any one particle and antiparticle finds each other, then they just annihilate back into like normal matter, like a gamma ray light, which will then create like electrons and protons and things like that. So that all happened, and then all that weird stuff is gone. But then you say, well, is there a loophole? And there's a generic loophole where things got dilute enough that these particles never found each other. And then if you turn the crank on that calculation, remarkably, it turns out the only condition to make sure that happened was that the particles were really small, and their smallness was the same as the smallness of a neutrino, one of the particles we actually know about and have. And the size of the neutrino is kind of a natural result of what's the weak interaction in particle physics. It's just one of the building blocks of our understanding of how matter is constituted in particle physics. So a weakly interacting massive particle is a particle that basically you just say, we think that it's the same properties a neutrino has. Neutrino, it turns out, a neutrino is almost massless. It's very, very light. Let's say it has about the mass of a heavy atom. And that's not random. We actually picked that because that's the energy scale or mass scale at which the mechanism that gives you the neutrino, the electroweak scale, exists. It didn't give us the neutrino, but it's one of the fundamental energy scales of the standard model. Yeah. And that's a really compelling story because especially at the time, we didn't have a complete understanding of that mechanism. And there'd been the hope that we were going to find new physics at the next round of colliders, like at the LHC when the Higgs was found, and that we would see a whole new set of particles when we accelerate to this new higher energy scale, which was just beyond reach back in the 80s when this idea came up, and that also that idea would provide the dark matter. And essentially, most people have looked for that form of dark matter since the late 1980s when the idea came out. Most people who said, I'm looking for dark matter, that's the type of dark matter they were looking for because it was kind of the most popular model.
So the neutrinos. So neutrinos sort of fit the model in some sense. But the wind is
neutrinos would be dark matter, but they're too light to actually work, and then so they just don't work as the dark matter.
Okay, so you had to go further away from neutrino to find something different.
We took the notion that neutrinos exist, and it gives us the fact that there are particles that are a certain size, but then by hand we said no, let's make them heavier, and so we constructed a model where there's a class of particles which are the size of a neutrino, but as heavy as a bunch of particles we do know about that we've created that are part of the electroweak mechanism that we call the electroweak structure in the standard model.
Yeah. So the wind. What is the scale that we are talking about? Like 1 giga-electron volt or something along those lines?
Right. So yeah, we like to use the giga-electron volt, but it turns out 1 giga-electron volt is also exactly the mass of a proton, right? The lightest atom. And so when we think of the WIMPs, it's not really constrained very well. It might be as light as about a GeV, and it might, for various reasons, we tend to think it's likely to be stopped up to about 100,000 GeV. But in principle, it even could be heavier than that. Big range of length scale, of mass scales that we consider. And yeah.
I mean, it's just amazing something that heavy could go undetected. So what's the mechanism there that, suppose it's 100 or 1,000?
Yeah. Let me say something. Okay, there's a weird thing, or there's just something in particle physics which is not our intuition, and it is the following: the mass of something and the size of something are essentially unrelated. And nothing in our normal everyday world is like that. Yeah. In fact, what do I even mean by the size of something? Okay, when you talk about a subatomic particle, it's actually a really weird thing. The basic fundamental particles we know of, the electron is 1. Proton is not. The quarks in a proton are 1, okay? Those appear to be point-like things. And by point-like, we don't really even understand what that means in some sense. It looks like the mass is somehow concentrated, or there's some infinitely small central identity to the thing, and then it has effectively a force field. And the size of it is essentially the extent of the force field, okay? The force field of electricity, in practical terms, is about the size of an atom. Proton has electricity, electron has electricity. They combine and form an atom, and the scale of that is essentially the strength and distance that that force field is effectively strong, and that's, you know, how the electron is bound to the proton and orbits it, or, you know, a nucleus which has a bunch of protons with neutrons and electrons, and they all orbit. So that's about an angstrom, you know, 10 to the minus 9 tenth of a nanometer. You know, that's the size of an atom. The nucleus is about 1,000 times smaller. Or sorry, 1,000,000 times smaller, 100,000 times smaller. And because it's dictated by the range of the force field that binds neutrons and protons together, and that's called the strong force as opposed to electricity. And it's a very strong force, but it's an unusual thing. It's very strong, but only over a very short distance. And that distance scale sets like what these particles do. Okay, neutrino has a very weak force and also a very, very short scale over which that field is there. So if I fire a neutrino at an electron, the electron has an electric charge, the neutrino does not. And what that means is that as far as the neutrino is concerned, the electron's electric force field just doesn't exist. The neutrino just doesn't feel it, doesn't know about it, okay? At the same time, an electron has this weak force field, and the neutrino has the weak force field. And those force fields have very short ranges, and so effectively, the particles are much, much smaller. You sometimes hear a statement, which is kind of silly, which people say, on a subatomic level, matter is mostly empty space. I don't know if you've ever heard that.
Yes,
Which is, it's complete junk, right? I mean, you know, if I fall down and my head hits the pavement, there's no empty space there, you know, it hurt, right? And that's because for the electric force fields, which basically determine chemistry, it fills in everything, you know, we're solid. But the strong force, which makes a nucleus do its thing, is 100,000 times shorter in range. So, you know, if I fire a neutron, which only fills in the strong force, at an atom, it just ignores the electrons. It ignores the electric force, and it has to hit dead onto a nucleus to bump into it. A neutrino is so small that if you tried to shield the neutrino, you go to the dentist and you get an X-ray, and they put a little lead sheet, it's maybe a 32nd inch of lead, and it totally stops the X-rays. If you wanted to put lead out to stop a neutrino, could you care to guess how much lead you need? Neutrino is really, really small. It has to dead onto the center of an atom. It's a light year.
A light year of lead, yeah.
A light year. A neutrino is mind-bogglingly, fantastically, stupefyingly small. And, you know, I'll throw out the number. It's like 10 to the minus 20 centimeters on a side. So its size is 10 to the minus 40 square centimeters. I mean, it's just not even intuitive. It's an incredibly small thing. And that's what we think the dark matter is. So even though it's heavy, it doesn't interact. It just whizzes around through stuff.
Right, right. Yeah, so that's an interesting thing, because our classical brains sometimes have difficulty understanding things outside our intuition. And so unless you have an electric charge, your behavior as a particle is going to be quite different, regardless of your mass or size.
That's right.
Of the particle.
That's right.
And so we've been seeking this WIMP construct for a while, and you've been involved with multiple experiments around this. So the latest one is the Lux experiment. This is in Utah.
Yeah, it's in South Dakota. Lux just completed, and the successor experiment is on the verge of turning on after 5 or 6 years of construction. We're all like, you know, in the last throes of trying to get it running, and it's going to turn on in the next couple of months, or imminently.
So what's the idea here? How do we detect a WIMP if it exists?
So the WIMP is basically, you know, we think it's the size of an atom, the weight of an atom, tiny, tiny, but weight of an atom. It's whizzing around the galaxy. It turns out we know, you know, the velocity of everything in the galaxy. You know, The galaxy is like a whirlpool and it's rotating. The velocity that things rotate is given by the gravity, which we sort of know. So we know how much, even if we don't know anything about the dark matter, we do know that the dark matter in the Milky Way is moving at a certain speed. Turns out it's about 1,000th the speed of light, which by the way, that's how fast the solar system is orbiting the center of the galaxy. We're almost a little bit relativistic. It's kind of fun. Yay us, right? We're going 200,000 kilometers a second around the center of the galaxy. Pretty impressive. Yeah. So the dark matter, whatever it is doing the same thing, although the dark matter is kind of it's not in the rotating disk, it's just rotating they're orbiting randomly. So we think of it as just particles hitting the Earth in all directions. There's this kind of weird thing about the dark matter. It's the dominant form of matter, yet obviously space is mostly empty. We tend to think that the dark matter is, especially if it's particles, it's diffuse. And in fact, it's a very faint diffuse cloud of gas, if you will. In fact, there's about as much dark matter as there are just atoms floating around out between the stars. Interstellar matter, it's called. Very, very faint, much lower pressure, if you will, than any vacuum chamber on Earth, or most vacuum chambers on Earth. Just a very low pressure set of particles. But they add up to be the dominant form. And as I said, since they're small like a neutrino, if they come at like your body or the Earth, they're overwhelmingly likely just to pass through unmolested. But occasionally they'll bounce off an atom and they'll deposit energy. It turns out if you work through that, the energy they have, given the velocity we know and the mass we sort of are guessing at, or we take a model, we say we think it's this mass, 100 proton masses for specificity, then you can calculate. And the answer is that the kinetic energy of these particles is about equal to low energy X-rays that you'd use for a dentist, again, just in X-ray energy. So what do? Well, you take a detector that could detect X-rays and you set it out and you say, well, did a dark matter hit it? Now, the immediate problem, because if it did, it'll bounce into an atom in the detector and it will cause disruption. And that's how we detect X-rays, and we'll use the same type of detector to detect the dark matter. All sorts of particle detectors, which is a whole rich other story, but just in a nutshell, they detect particles because we're talking about particles that have a lot of energy. They're not like room temperature, just floating around. They're coming with quite a velocity, 1,000th the speed of light. They smack an atom, and the atom will get hit hard. It's like a super fast bowling ball hitting a sea of bowling ball, billiard pins, and just causing havoc. And it'll ionize electrons, it'll ionize atoms, it will make atoms fluoresce and emit light. And in certain materials, you can measure the electrons, you can measure the fluorescence, and you can build a detector. And there's a 100-year history of people figuring out how to build good detectors. That's my stock and trade, is building detectors that can detect that the dark matter hit the detector.
But the problem is we have a lot of extraneous radiation, right? So the Deluxe design, if I understand this, Tom, so this is in South Dakota. You had to go a mile down
Yeah.
to some sort of a gold mine or something like that?
We have to go to enormous lengths to remove radioactivity in any way, shape, or form. So all the materials in the detector have to be super carefully selected not to have radioactive elements. Turns out uranium and thorium and potassium are left over from the formation of the solar system, and they're all three radioactive. Even potassium, which is a common biological element, is weakly radioactive. So we have to make sure our everything in the detector doesn't have that. And so there's this whole chemistry and kind of black magic, or just understanding all of that. And people have been going at this sort of experiment for about 40 years now, and there's a whole body of knowledge of what to build out of the detectors. Yeah. And then a separate thing is you put a lot of shielding. So like dirt is radioactive, and we put shielding material between the outside world with dirt. It doesn't matter if it's your house or the outside or underground. It's all about the same. Just radioactive decay in rock. So you put out shielding. In our case, we use water. It's not a very effective shield. Lead's a nice effective shield. Lead's, it turns out, is the chemistry of lead is it can be low background, but it's kind of ugly to mess with. So we use water, and you do a lot of water, but water's cheap. And it turns out people are good at purifying water. It's actually hard to purify water because water is a solvent, wants to dissolve minerals and stuff. But dirt cheap in relative terms, you can get super good water purification because, well, we drink it, right? And we all figured out how to, so we have a large water tank. It's like 8 meters in diameter, 20 feet in diameter, 20 feet tall. And in the center is a detector. And then all that water just stops all these gamma rays and neutrons coming from radioactive decay. But then there's a second piece of the story, which is that there are high energy particles from exotic processes throughout the Milky Way and throughout the cosmos, in fact, literally from black holes, from supernova, et cetera. All these high energy particles, it's kind of a low rate at some level, but it matters for us. They hit the upper atmosphere and they cause these showers of particles. And those are kind of murderous if you set your detector up on the surface. You set the detector up on the surface with no shielding, you're just wiped out. Literally, like, the rate in the detector is 1 trillion times higher than we can tolerate in our dark matter search. 1 trillion, some number like that. It's a fantastically large number. Every 5 years I go recalculate it. It's like, wow, that's a big number. So we got rid of most of it by shielding and selecting materials. But then the stuff from the atmosphere is not easily shielded. This one particular particle called the muon, which is it's a clone of the electron. It's heavier and it decays after a little while back into an electron, but you can create them through high energy interactions. Those will go like a mile through rock. So we find there's a handful of deep underground sites worldwide where these experiments are carried out. We're in the famous storied Homestake gold mine that was the source of gold in the South Dakota. It is Hearst Sr., the one before the newspaper magnate. That's how he made his money, was this mine in South Dakota, the biggest gold mine in North American history. And it shut down in 2002. It had a famous experiment that detected neutrinos from the sun, by the way. And so we're in the location where that neutrino experiment was there. It was turned into a science facility during the course of the decade of the 2000s. It was a big, interesting political, sociological backstory to all that. There was a governor Governor Rounds actually made it happen. And anyway, and so there's an underground lab, and we have our experiment there.
So you started in 2018?
Sorry. The effort to turn that into a lab goes back into the middle of the 2000s. I was on the Lux experiment, which was the first experiment at that lab, and we started Lux in like 2006. We took data in 2013, ran for 2-3 years. We got money to fund the current experiment starting around 2014, and we've been constructing it ever since, and we're in the final throes of about to turn on.
The current one is bigger in terms of the detector size?
So what's been happening is you put out a detector and you wait and you hope to see the dark matter, and you go a few years and you haven't seen it. Unfortunately, so far no one's seen it. You can wait longer, but almost always you know how to build a much bigger detector. So essentially what the field has been doing is various experiments. It's very competitive, by the way. We have a very serious competing experiment in Europe, which is very similar. We kind of all know each other, go to a conference, we all hang out, but, we go back to our lab, we're all, it's that's real competition. They're actually turning on just about now as well. Anyway, but you can basically most new generations have built a detector which is about 10 times bigger than before. We are now at a scale where the experiments, just the construction is in the many tens of millions. So you don't easily just go get enough money to build the next experiment. The 2 current experiments, which are about to turn on, are both around 10 tons. I actually started my entire career in this field when the whole idea was new. And at the end of my thesis, we had delivered a 60-gram detector. So I have ridden this tiger from 60 grams now to 10 tons.
10 tons.
Yeah.
So how long do you think you have to go, Tom, before you can reject? Let's say I don't want to be pessimistic, but suppose you don't find anything. How long do you think you have to go to reject the hypothesis?
It's not a look. This part's not a happy story. First off, the answer is you can't. You don't know. If we don't find it, we don't know. And there's a piece to it which is interesting. It gives us closure, but is a little, from a philosophical perspective, is obviously not very satisfying. If we succeed in building a detector, if we don't see anything with this next generation, which has a nice bite at the apple, by the way, we're actually going to be, we're 10 times bigger and we're lower in background, such that we think we're going to be about 50 to 100 times more sensitive than previous experiment, our previous experiment. So that's a nice chance. We essentially, we can see particles that are up to almost 100 times smaller than is the current limits.
Yeah.
Oh, and by the way, since I entered the field as a grad student, we have improved our sensitivity by about a factor of 1,000,000. So we're right now probing particles. The thing we're probing is, are they smaller or smaller or smaller? And we don't have a good theoretical prediction from how big they are. We said it was like a neutrino. Unfortunately, the WIMP story, all the modeling I've talked about, the analogy from particle physics, it only gave us a very broad guideline that it's about the size of a neutrino, plus or minus 5 or 6 orders of magnitude. So, yeah. And on the minus side, the theorists can always tune the damn thing down to 0. So they keep saying, "Oh no, keep looking." Okay, so we've been searching. I know I've given that was a big mouthful. Let me try to pull this back together. So we're about to get another big bite at the apple, where we're going to move somewhere between a factor of 10 and 50 in size range, and maybe we'll see it.
Yeah.
And then if we don't, a final experiment, which we're already starting to plan. In fact, we just signed a memo to work with our competition because we want a lot more money. We got to work together. And we're going to hopefully build a final. It actually probably would be a final experiment, be about 10 times bigger, maybe 50 times bigger. We're about to run out of money that people will want to put into this idea, okay? There are practical, you haven't found it, it is speculative. It doesn't make sense to put $10 billion into it, right? Current experiments are about 50 million, and probably a final experiment is going to be in the scale of a few hundred million. Secondly, we will run into a residual signal in the detectors, which is due to a known source of neutrinos, which will mimic the signal from the WIMPs, and is in practical terms we can't get around it. Given infinite money, we could build a very sophisticated detector that could get around it, but in practical terms, I don't think that's ever going to get funded, or at least not in my lifetime. So we're near the end of looking for what I have been looking for since I was a wee lad.
Yeah, I mean, the beauty of the WIMP, if I understand this correctly, Tom, is that it solves a lot of problems, right? Not just this issue with the rotation of the galaxies and the stars,
Yeah.
but it also plugs some holes in the standard model, I understand. But if you fail there, if you go further down the spectrum onto the right-hand side, I know there are machos there and other stuff there. Do you think any of those things are compelling enough to really look?
Well, okay, so the thing is, on the heavy side, especially when you think about something like a planet and black hole, right? That's compelling because there are planets and there are black holes. We know that. So maybe they can somehow be the dark matter. The thing is, if it's planets or black holes that grew in a normal way, I didn't go into this, but we can detect the presence of the dark matter in this really early time in the universe, measured through this what's called the cosmic microwave background, and that's a whole story in cosmology.
Yeah.
And we can tell the dark matter was there, and we could tell how much there was, and we could tell how much normal matter there was. The normal matter formed all the planets, and we can already see that doesn't work. In other words, if it's something the size of a planet, it can't be made out of planet material. It's not made out of rock, or it's not made out of gas like the big planets. It's made out of literally an exotic thing. And it's kind of odd, given that we know there's all sorts of exotic particles. It's just so natural to think any new form of matter is particles and not super heavy things. Those heavy things would have had to have been formed early in the Big Bang through some physics mechanism we don't know. Now, theorists are clever people, and they have a whole, there's many papers on mechanisms to create planet size or star size things that look like maybe they're a black hole today, or they're just some inert object. And it could well be that that's the dark matter. It turns out experimentally, you can rule out a whole raft of those sorts of models because if the dominant form of matter in the Milky Way is these big, heavy star-like objects, they actually will have effect on the motion of other stars. And it's a complicated story, and people continue to work on that. And wide swaths of ranges of masses of planet-like things, or Manhattan-sized things or Connecticut-sized things are ruled out. But then there's certain size scales. So I don't know, Palo Alto-sized things are allowed. And people think about that. And look, I'm not going to shoot arrows at anyone who wants to explore a version of dark matter that's not the standard WIMP story, because frankly, we've gone 6 or 7 orders of magnitude. We haven't found it. We have a little bit more to go, and then we're going to be able to, we have to stop looking because we can't look any harder. That's why people are thinking about it. Well, people have been thinking broadly for a very long time, but frankly, the WIMP paradigm absolutely ruled dark matter detection for the last 30 years. And that era is kind of coming to a close. So I'm in the closeout set of experiments and looking for WIMPs, and now people are thinking more broadly. And there is you mentioned axions, and that's a whole story. There essentially were 2 holes in the standard model that people realized early on were natural to think of as candidates for the dark matter. One was the WIMPs, the other is axions. Now, there's in fact many other ideas you can get out of the standard model, but for a variety of reasons, people felt like those were the 2 compelling ones. The axions kind of languished until recently, and now there's this huge renaissance of let's look for axions, and there's a whole explosion of experiments that are looking for axions. The techniques are extremely different.
Is it experimentally possible?
Oh, no. Well, the way it's going to work is you can kind of see how to do a lot of it, and then you can see if I really, really improve things, how I'll do further. And all of that is getting going. There's only really one axion experiment now that is sensitive enough to probe any reasonable you effectively are looking for a signal where in a very strong magnetic field, which you have to create through binary. And there's this very interesting convergence of very sophisticated sensor techniques that use quantum superconducting effects, and people call them quantum. And in fact, they have the technology has been driven by the explosion in quantum computing, which is solving a lot of nuts and bolts engineering issues to make this stuff practical instead of extraordinarily difficult, because you have to build everything by hand. That's really, it's interesting that as people have decided it's important to look more broadly than WIMPs, that type of technology has really gone through a huge evolution, and it is going to enable a whole wave of searches for axion-like particles. And that's a really long and interesting story. And those are fun because they're small experiments. When I got in this field, it was like 5 people were an experiment. LZ is 200 people. Our competitor is 200 people. This new thing we're going to form is 500 people. The axion experiments are now at the beginning of that whole process, and someday they're going to be big experiments. Hopefully, someone finds the dark matter.
Yeah, it's an important question, right? At the very high level, we don't know. I mean, we know only 5% of the universe, so to speak, and this 25 to 27%, which we believe is dark matter, we still don't have a clue. So it's really a very fundamental question, and if we cannot answer them, we cannot go anywhere. And it is a very interesting experimental question because there are a lot of hypotheses in hundreds of orders of magnitude of different things, but we haven't found anything. So in some sense, Tom, this makes the field interesting. Hopefully it'll get more graduate students into the field, and they'll find new things and new ideas and new ways to look for things, hopefully.
Yeah, it's a thriving field. It's just hopefully the day will come when someone's going to find it, and that'll be a time to rejoice. We don't know when or where that's going to come.
Excellent. Yeah, this has been great, Tom. Thanks so much for spending time with me.
Yeah, so this is very enjoyable, and nice talking to you. Bye-bye.